Dynamics is finite dimensional, but what you're doing is, originally, when we looked at stability of a trajectory, we had three coordinates, x, y, z. We looked at a trajectory, and that had three eigenvectors locally. So there was a Jacobian that told me if I started here, how the neighborhood went. The Jacobian was 3 by 3 matrix, and there were three eigenvectors. Now we are doing something totally different, which is in 3 dimensions, and now I can draw this, so I'll just draw only 2. So here's dimension x1, x2, x3. So that's the space on which I define a function phi of x. So that's a function. So what evolution operator does is it maps this function into another function. Because this is a function, it takes infinitely many numbers to specify it. It's defined every place. So the way you usually learn how to do them is you use a basis. You use Chebyshev polynomials, Fourier, some basis. If you do it as a basis, let's say Fourier basis, just make it very simple, and this is infinitely many numbers, phi k, complex numbers with things that have to do with 3 dimensions, let's say kx. If you're in 3 dimensions, I or 2 pi or whatever, right? So then operator acts on these guys, if I'll also express in Fourier basis, but there are infinitely many of them. So there'll be infinitely many, not 3, but infinitely many eigenvalues. So it doesn't matter what underlying space is 1, 2, 3, or 1,000. This always will have infinitely many eigenvalues because it acts on functions. So this seems like not a very wise thing to do because we started in 3 dimensions, so why are we screwing around in infinitely many dimensions? It pays off because linear algebra is so powerful that it'll give you a good spectrum. So even though the problem looks difficult, you'll actually get very good calculation of the spectrum. And what we will do is we will compute this spectrum on the left-hand side. We'll compute it on periodic orbits, which we control totally. So we'll actually compute these things using the right-hand side of equation. Now, anecdotally, one of the pretty things about quantum mechanics, this theory works also for quantum systems, not classical. I'll only describe it for classical. And experimentalists cannot see classical electron trajectories, but they can see spectrum because they're very good at measuring spectra. And they shine light on hydrogen in magnetic field and they see lots of absorption lines. So they're extremely good in computing these guys. So one of the very cute things from the 80s, early 90s, atomic physics experiment actually measured the classical orbit of electron by reconstructing it from the phases. So they actually measure that the electron goes out and does this and comes back to the nucleus in a given time that you can compute because you have your equations, but they measure it by looking at the spectrum. Sometimes you go from spectrum to space. But what we'll do is, because we have very good local control, we'll compute this and from it we'll get the prediction. And that's a global prediction for infinite time, and this is finite time calculation.